If you go out to the beach and it's been a hot day and you put your toes into the sand, you might find that the sand's really hot. If you put your toes into the water might be warmer than normal water that you're used to, but it's not going to be the same kind of hot. They're both subject to the same amount of sunlight and everything, so there is a question of why is the sand so much hotter than the water? And the answer deals with something called heat capacity. Heat capacity gets a lowercase letter c, and it's a measure of how much energy it takes to raise 1 kilogram of a certain material by 1 degree Celsius, or by 1 Kelvin. So C gets units of joules per kilogram Kelvin, or kilogram degrees Celsius if you like. Water is what we end up using the most, and water has a heat capacity of 4186 joules per kilogram Kelvin. If you have seen this in a Gen Chem class, you might be used to seeing a number like this, 4.184 joules per gram degrees Celsius, or 4.186, sorry, joules per gram degrees Celsius. If it takes 4-ish joules to raise 1 gram by a degree Celsius, it's going to take 4,000 to raise 1,000 grams 1 kilogram. The only downside to starting with water is that it gives you kind of an unreal sense of scale. So if you start looking at some other materials, aluminum has a heat capacity of 900 joules per kilogram Kelvin. Gold has a heat capacity of 129 joules per kilogram Kelvin. Even wood, and yes, there are many different kinds of wood, so there is some amount of ambiguity here, but a reasonable estimate on wood, or a reasonable average, is about 1700 joules per kilogram Kelvin, which is still a smaller number than water, right? We are talking less than half of the heat capacity of water. So when we have this heat capacity for water being 4,000 joules per kilogram Kelvin, that's a lot. It's a big number. What this means is that if I have 1 kilogram of water, it's going to take 4,000 joules to heat that up by 1 Kelvin. If I have 1 kilogram of gold, it's only going to take 129 joules to heat that one up. So heat capacity is a measure of how much energy is required, and a higher heat capacity it takes more to heat it up. So a higher heat capacity equals increased resistance to temperature change. I started off by giving you an example of the beach, so I think it makes sense to give you that number too. Sand, which again, like wood, there are many different kinds of sand, but sand is somewhere between 800 and 1200 joules per kilogram Kelvin. So a bit of sand that gets the same amount of energy as a bit of water, the sand is going to change that temperature, or the sand's temperature is going to change a lot more drastically. There is one thing that happens, and that's a little bit unfortunate. This is called heat capacity. There's a different thing that we call specific heat. And it's very similar. So specific heat is all about having one particular item. If I have a cup, and I'm going to fill it with different things, but whatever the cup itself, I don't need to necessarily have, if this is an aluminum cup, I don't need a joules per kilogram degree, or per kilogram Kelvin, because the cup itself isn't really changing its mass ever. So if I could just have like a joules per Kelvin for this thing, then I don't need to refigure out the mass and remeasure the mass every time. you will see different textbooks, different sources use different letters for this idea of specific heat. Sometimes you will even see specific heat capacity. A lot of times we see a capital S or we see a capital C. I'm going to avoid using it a little bit. I'm going to just call this thing specific heat, and that's going to have units of joules per Kelvin. There is a question that's easy to ask of how do I know which one it is I'm dealing with, but the units on these things really give everything away. If you're given a number that is in joules per kilogram Kelvin and you are asked to find like a heat in joules, I'm going to say I've got joules per kilogram Kelvin. Well, I need to multiply that thing by kilograms, then those can drop, and by Kelvin, and then those can drop. Kilogram sounds like a mass. If I'm multiplying by Kelvin, that's a temperature change. And this thing is a heat capacity. Now I'm looking at a heat exchange. If I'm given a number that's in joules per Kelvin, and I am asked to find a number that's in joules, all I have to do is multiply this thing by a temperature change, because the temperature change will be measured in Kelvin, and those can cancel. So then I'm saying Q equals, if we're calling this thing S, we're going to multiply that by delta T. I'm a little hesitant about S because we end up using it for entropy really, really soon. So maybe I will say Q equals temperature change times specific heat, and write it that way, and that's going to have to be probably as well as I can do with that. That's the idea of temperature change. One thing we do with this a lot is called calorimetry. Calorimetry says this: I would like a closed system, so maybe I've got that same cup again, and inside here I have some water that is sitting at 20 degrees Celsius. I'm going to add into here maybe a little metal cube that I've got, and that metal cube is sitting at 50 degrees Celsius. And then I'm going to put a cap on the whole thing. What we know is that over time, these two will equilibrate. They will reach one common temperature. So what I need to do is figure out what temperature that is. I'm going to look. The cube is going to lose heat. So that's going to have a Q equals mass of the cube heat capacity of the cube times the temperature change for the cube. This is the heat given off by the cube. Now the cube is going to go down in temperature, so temperature change right here is going to be a negative number. I would like that, all the heat that gives off is going to be picked up by the water. So I'm going to have mass of the water, C of the water, times the temperature change of the water, and that's equal to Q here. The problem here is that the temperature change of the water, this is going to be a positive number. So in order to make this work, I need to throw a minus sign on there. And that's my basic calorimetry equation. I'm going to end up using it quite a bit. I will work through a problem that shows you this as a more careful example, but for right now, that's it.